Hello everyone, my name is Lucas and welcome to the Intellectual Bookshelf. Few areas of mathematics are as beautiful as differential geometry, in my opinion. But they're also almost the easiest to introduce in a way that feels mysterious and unmotivated, And that's a problem. But Manfredo de Carmo's differential geometry of curves and surfaces takes exactly the opposite approach. And, rather than asking you to accept the abstractions from the very beginning, it just builds the subject very patiently, one geometric idea at a time. So today I'd like to tell you why I believe this book has remained a classic for nearly 50 years. But before talking about the book itself, let me just say a few words about its author, Manfredo Perdigão do Carmo. And he was a Brazilian mathematician. He was born in 28, and unfortunately he passed away recently in 2018. He was definitely one of the central figures, contributing to the early dissemination and development of mathematics here in Brazil, together with Leopoldo Nachbin, Maurício Peixoto, and Jacob Paulis, and also Elon Lages Lima. Actually, I am going to be talking about some of Elon Lages Lima's books in future videos. He has lots of nice books on analysis, topology, and metric spaces. Anyway, Manfredo concluded his PhD in '63 at Berkeley University under the supervision of none other than Professor Chern. He was emeritus professor at IMPA, which is the Institute for Pure and Applied Mathematics here in Brazil. He was also president of the Brazilian Mathematical Society, and he wrote other books, such as Riemannian Geometry, which is from '79, and Differential Forms and Applications from '92. This book right here was originally published by Prentice Hall in '76, but the Portuguese version I own was actually published in 2005. But my copy is from 2014. Now let me tell you a personal story of how I got to do Carmo's book. I was starting my master's studies in theoretical physics, and although not necessary at the time, I wanted to learn differential geometry from scratch, and I wanted to do it with a pure mathematical approach, which I thought would be much cleaner, since most books I used were devoted to physicists like, Nakahara and other books, and proved very few things and were very informal. So I picked Warner's book, Foundations of Differentiable Manifold and Lie Groups. I do not own the book, but I remember right in the first pages, Warner would define a manifold as being the second countable Hausdorff locally Euclidean, with a differentiable structure on it and something like that. I don't remember exactly, the precise definition Warner uses, but it may be slightly different. It doesn't matter. What it matters is that I thought, okay, why second countable? Why Hausdorff? And so on. So I wanted to have an intuition of what was going on and not just accept it and move on. So I actually got stuck there, and after some weeks, I couldn't, move on, and I gave up. So later I came across the do Carmo's book, and it was exactly what was missing for me, Now I could understand things gradually, and no fancy name was introduced that was not completely explained. I could finally understand it now, and I couldn't before, because I was not at Warner's level, maybe, background-wise. But perhaps looking back, I don't think the issue was mathematical maturity alone. I had already studied tensor calculus, complex analysis, Fourier analysis, linear algebra, and group theory. What I lacked was an intuitive understanding of why differential geometry begins, with such abstract objects. So that's how I came across do Carmo's book, and in many ways it completely changed how I approached differential geometry. By the way, if you're enjoying the video so far, and you'd like to see more reviews of great mathematics and physics books like this one, consider pressing the like button and subscribing to the channel. It really helps the channel grow and lets me know you'd like to see more content like this. Now let's take a look at what you actually learn from this book. Okay, so the prerequisites here needed for this book, Manfredo essentially says that, well, essentially linear algebra, and multivariable calculus, and that is already a big difference with some other textbooks on differential geometry. As I'm going to show you some other textbooks on differential geometry, on modern differential geometry, that will require a solid understanding of analysis, topology, and even algebraic topology to even start reading the book. Now, here you may notice the progression, right? The book starts with curves, objects we can visualize immediately, and then moves on to surfaces, then to curvature, and to intrinsic curvature right here, and then to global questions, right? So now you have the background needed, right? So assume you have the background needed. You've already seen curved surfaces from calculus. You are familiar with the concepts like tangent line, derivatives, length of a curve, area of a surface, normal vectors. The most interesting fundamental questions, like what it means, for a surface to bend, or how can we measure the curvature of a surface? When are two surfaces geometrically the same? How can we tell whether, for instance, someone living entirely on a surface could detect that it is curved? Is it possible? How would that go, right? I think this book is like a continuation of calculus. Things that were left unsaid, that could not be treated there, now have a full theory that explains it. And Carmo starts with the basic idea here of a curve, as I mentioned. Then you get to the notion of curvature and torsion of a curve, and suddenly, boom, you get to the Frenet frame and fundamental theorem of the local theory of curves. It's completely characterizing any curve in terms of its curvature and torsion, apart, of course, from rigid motions, rotations, and translations. Now that we have mastered one-dimensional objects, so the next question would be, okay, and how about 2D objects, right? And how about two-dimensional objects? Yeah, surfaces. Well, how can we completely characterize it, its properties and invariants? And then the book starts with the basic ideas here on regular surfaces, and arrives at the notion of the first fundamental form, which is an intrinsic geometry property of the surfaces, encoding things like angles, distances, and areas. So the first fundamental form actually encodes quantities you can measure from within the surface, right? So the next question that arises here is, how about the bending, bending of a surface? How do we measure that? For instance, could an ant living on the surface of a sphere with very large radius, for instance, tell it apart from a plane, for instance? Well, it turns out that the ant, let's call him George, or let's say, okay, so George would be able to determine whether it lives on a surface of a plane, or if it lives on a surface of a sphere, which is beautiful and very surprising fact. And that was stated and proved by Gauss in the so-called Theorema Egregium, which literally means remarkable theorem. And that is honestly how I felt about the theorem as well when I was first learning the theorem. Now, the funny thing is that although George could tell a sphere from a plane, he would not be able to do so for a cylinder and a plane, for instance. The Gaussian curvature is 0 for both surfaces, for both the plane and the cylinder, right? There is no stretching here. So you might say, okay, but if you show me a cylinder and you show me a plane, I can definitely tell you which is which. Yeah, you can, but that is because you are looking at them from outside, And this is where the second fundamental form enters the picture here. So it actually measures the intrinsic geometry of a surface, right? So how the surface somehow sits inside an ambient Euclidean, the ambient Euclidean space. Through it, we define concepts such as the principal curvatures and the mean curvature, quantities that generally distinguish a plane from a cylinder. Okay, and then finally here, he's in chapter 5 is Manfredo starts talking about global questions, right? For instance, what if you have a surface that is everywhere, that has positive Gaussian curvature everywhere, for instance, and all these type of questions naturally emerge, and then he discusses many important things. And so in chapter 5, you already have the Gauss-Bonnet theorem, which is a very beautiful theorem as well. And then finally, Manfredo starts talking, about a global differential geometry. Questions like if you have a positive curvature, everywhere in the surface, then what can you say? What can you tell about that surface and things like that? And so global questions appear in chapter 5. Okay, talking a little bit about the style of the book. Well, every chapter is divided into sections, and there are exercises, many exercises at every section. For instance, you have section 2 here. There are many beautiful images too, many beautiful images, and you see there are exercises for every section. Okay, and this is good because you can check whether you're understanding the subject as you go through the exercises, and get to the next section. It feels like a small victory. So I highly recommend you to not skip the exercises. Go through at least half of them, in my opinion. Ideally more than 75%, I would say. But so there are easy exercises, there are medium and hard exercises. There's no modern differential geometry subjects here, like differential forms, vector bundles, which for me is not a weakness. It really is not a weakness. It's a choice. It's De Carmo's choice, and I think it was the right choice for this book. Well, some people don't like the book because it is too extensive. It's more than 600 pages. Yeah, it's more than 600 pages. But I do. I think it is rigorous where it needs to be rigorous, and it is a little bit more informal where it is necessary, in my opinion. So let me briefly skim over the book so you can see, the style. This book, as I mentioned, is originally from 76. Yeah, 76 or 79. Don't recall that, but I said it in the beginning. I think it's 76. And yeah, so you have many calculations. Now, I would like to mention, if you're going to study this book, there is a very nice course that is available on YouTube by Claudio Arezzo. It's from the International Center for Theoretical Physics in Italy. It's ICTP. It's a course on differential geometry that actually Arezzo uses this book as a textbook. I will leave the link in the description as well. I'm going to mention some other books I have that are somehow related to this book, that are similar to this book. Differential Geometry by Paulo Ventura Araújo. I have the Portuguese version here, but there is an English version. I'll leave a link in the description as well. Now, I haven't really used this book, but I can tell you a few things. The book covers essentially the same material. It is like 1/3, 1/3 of the size of De Carmo's book. De Carmo's book has more than 600 pages, and this one is close to 200 pages. It must have a faster pace, right? But I have heard nice things about the book. So as soon as I can take a closer look to it, I'll make a review video for you guys. Manifolds and Differential Geometry by Jeffrey Lee. This is definitely a more advanced book. It's a book on modern differential geometry, let's say. So it should definitely not be used if it is your first time studying differential geometry, in my opinion, right? I suggest going through curves and surfaces first, using De Carmo's book, for instance, or even Araújo's book. You'll find here more advanced topics like Lie groups, fiber bundles, differential forms, even Riemannian and semi-Riemannian geometry here. So for this book, I think you should have a solid understanding of algebra, okay? Groups, rings, modules, all these all these things. Also a solid understanding of point set topology, and at least the first course in algebraic topology, I think, covering homology, homotopy, at least the basic stuff. The last book I want to show you is this book, The Introduction to Smooth Manifolds by John Lee. And no, Jeffrey Lee and John Lee are not related, as far as I know. Okay, this book I think is easier to follow than Jeffrey's book, although they have a great amount of intersection, of topics. There are some topics from Jeffrey that are not in here, and vice versa. And it is best if you have the prerequisites I mentioned before for Jeffrey's book. If you have the prerequisites for this book too, this book has appendices reviewing topology, linear algebra here, and calculus, and also differential equations. So it is a bit more self-contained, I would say. Furthermore, John has 3 other books that complement each other, which is the introduction to topological manifolds, I think, introduction to Riemannian manifolds, and introduction to complex manifolds. But unfortunately, I do not own any of these books. And also, there's this book by Manfredo I mentioned in the beginning on Riemannian geometry, which I shall be talking about in future videos, but it's on Riemannian geometry, so I'm not going to say anything else on it right now. By the way, if any of these books look interesting to you, I've left links to all of them in the video description, including de Carmo's book, in case you'd like to add them to your own intellectual bookshelf. Now, looking back, I don't think what I needed, back then was an easier book. I needed a book that explained why differential geometry is built, the way it is. And for me, this book, Differential Geometry of Curves and Surfaces by Manfredo do Carmo, did exactly that. And that's why it remains one of my favorite mathematics textbooks. If you've read this book, I'd love to hear your thoughts. Or perhaps you learned differential geometry from a different book. Let me know in the comments, okay? And if you enjoy discovering great mathematics and physics books, consider subscribing to the Intellectual Bookshelf. Thank you very much for watching, and until next time, happy reading!